At this point, we'll dive into the most interesting aspect of the resource bind model, and that's how we deal with the shader visible descriptor types: constant buffers, shader resource views, unordered access views, and samplers. So we want to be able to quickly, cheaply set up the set of textures and so on that each draw or dispatch is going to use, and maybe even be able to select which descriptors we use right from within shaders. And we want to be able to have our descriptors wherever we want and however laid out in memory however we want. So the first step in this process is defining a map that identifies to the driver shader compiler what convention you as an app have chosen in laying out your descriptors so that shaders know where to look to find resources. The name of the resource binding layout definition in DX12 is the root signature. So why the name root? Think of it like a plant where the root system provides nutrients to the plant. Correspondingly, in DX12, the root provides memory to the shader pipeline. And the structure of the root turns out to have branching in it, representing levels of indirection. And the signature of the root defines the structure of the root system. So the root signature is a completely user-defined map identifying to shaders what type of resources they should expect to find and how they'll be arranged in memory. This definition, sort of like a function signature in C programming, is abstract in that the memory locations being referenced or the contents of that memory aren't defined yet. Just the layout of the data structure is defined. The root signature definition actually gets compiled directly into shaders so that drivers actually hard code the traversal through the signature directly into each resource reference into the shader. Just like how in a function signature there's a set of function parameter declarations, in the root signature there are a set of root parameter declarations, where each parameter declaration is abstract in that it defines only a type, but there's no memory or data associated with the parameter yet. In a C program, when a function is called at runtime, its parameters are filled in with arguments, which are the concrete values passed into the function. Similarly, in DirectX, when the root signature is used at runtime, its parameters are filled in with root arguments that define what shaders see when they execute. So changing the root arguments changes what shaders see during the flow of an application in DX. There are three types of parameters that can be used in a root signature: a descriptor table, which is a pointer to a set of descriptors in a descriptor heap; a root descriptor, which is a descriptor directly in the root arguments; and root constants, which are numbers or constants directly in the root arguments. These three types of parameters will now be described in more detail. A descriptor table declaration in a root signature is a set of ranges of descriptors along with, for each range of descriptors, the HLSL bind name for the start of the range. The set of descriptors in a range defines a contiguous set of bind names. Also not shown in these diagrams is an additional parameter in the descriptor table declaration, which is the shader visibility, that declares which shader stages can see the bindings defined in the descriptor table. At execution time, a descriptor table root argument is just the pointer into a descriptor heap that tells the shader where to find the range of descriptors declared in a descriptor table. A root descriptor declaration in a root signature consists of simply a selection of descriptor type along with HLSL bind name and shader visibility. Now, the set of descriptor types that can be used with root descriptors is limited to only constant buffer views and raw or structured buffer UAVs or SRVs. So, most notably, more complicated descriptor types, such as, for example, a texture 2D shader resource view, can't be used with root descriptors. And the reason for that is the way that root descriptors are represented at execution time as root arguments is simply using a GPU virtual address to the start of the data in memory. That is what the descriptor is, as opposed to the descriptors for views that live in descriptor heaps, where the hardware supports a more rich descriptor definition. So for example, a constant buffer view descriptor in a descriptor heap can contain a size which would allow for out-of-bounds checking by the hardware if the shader is asked to read out of bounds of the range of memory described for the constant buffer view. So in contrast with a root descriptor, since it's just defined as the base GPU virtual address, obviously the hardware can't do any out-of-bounds checking. A root constant declaration in a root signature consists of a count of constants, an HLSL bind name, and the shader visibility. At execution time, the root argument is the set of 32-bit values defining the constant, and you're allowed to actually change just a subset of values at a time if you want. You've seen that every root descriptor declaration includes a shader visibility declaration. The options are shader visibility all, which asks the hardware to broadcast each root argument to all shader stages. So that allows you to just set a given root argument once and have the hardware broadcast it. The other option is per stage shader visibility, like shader visibility vertex or pixel and so on. One use for this second option is, suppose you have an existing HLSL suite where, say, register T0 in the vertex shader expects a particular type of resource, whereas the same bind name T0 at the pixel shader expects something else. Using this per stage visibility allows distinguishing different bindings to the same bind name at different shader stages. Now, shader visibility all with T0 in this case would conflict with per stage visibility for T0, so combining these all with a per stage visibility at the same bind name would be an invalid root signature. A root signature declaration includes a few miscellaneous options exposed as flags. One of them is allow input assembler input layout, so that means you opt in to using the input assembler. The reason for that is if you need to use the input layout, which defines a set of vertex buffer bindings, some hardware implements those bindings using one of their hardware native root argument slots, sort of like a hardware descriptor table. And so what that means is that there's slightly less space for the hardware to efficiently store your user-defined set of root arguments. This doesn't take away from the total amount of root argument space you have, because the hardware can spill to slightly slower memory. Some details of that are described later. So this is really just a sort of a minor optimization, not particularly important. A similar example is allow stream output. Another flag that can be specified is deny vertex, hull, pixel, or whatever shaders root access. So if you know that you are never using, for example, the tessellation shaders hull domain, you can specify in a root signature to deny root access from these shader stages. Or if you happen to be using these shader stages and you know that it's such a simple shader that it doesn't need any resource bindings at all, not even constants, then you could also specify, the root signature could also use these flags. The value in specifying these flags, it means if you specified visibility all for a root argument, so in other words, you've asked for a root argument to be broadcast to all shader stages, some hardware that has to take a cost that is proportional to the number of stages that an argument is being broadcast to can limit the amount of work that's needed to just the necessary stages. So you could do use visibility all and a selection of deny flags to turn off shader stages you aren't using, so that you end up with, for example, a broadcast of one root parameter to just the vertex shader and pixel shader if those are the only shader stages that you need to use with a given root signature. There's one more component of a root signature that hasn't been mentioned yet, and that is static samplers. These are samplers that are fully defined in the root signature, and so they're different from all the other root parameters where there's a parameter declaration and at runtime the arguments or values for the parameters are set. In this case, the sampler is fully defined and baked in the root signature. There's no downside to using a static sampler versus a sampler in a descriptor heap. The case for having descriptor heap samplers is that you might want to dynamically select which samplers that you want to use with a given shader. But if it turns out that you know that your entire application, or at least the shaders for a given root signature, will only use some small set of samplers, you can just get away with defining them all statically. Another advantage of using static samplers is that, as you will see, root signatures can be declared in HLSL. And by extension, then, if you can define static samplers in a root signature, you can now define static samplers directly in an HLSL program. So you can have samplers fully defined directly in the shader that uses them. It's also allowed to combine the use of static samplers and samplers from a descriptor heap in the same root signature if you want. Let's talk about how root arguments are stored. On some hardware, there's actually dedicated space for storing root arguments that's very close to shaders. You could think of them like being shader registers. There's about 16 D words, at least on current hardware. But it turns out not all of those 16 D words are available to the app directly, because the hardware has to use some of the space for its own internal purposes. One example of that was actually covered a couple of slides ago, where if an application is using the input assembler input layout, this hardware has to use one of the D words to implement a pointer to essentially an internal descriptor table representing the vertex buffer bindings. It's actually possible for this hardware to support larger root signatures than the native size by simply spilling to slightly slower memory for arguments that go beyond the native root argument storage space with large root signatures. On the other hand, other hardware is more flexible in that it doesn't have a hardwired root argument storage size. The way to think about how root argument data is managed by the driver and hardware is that anytime any individual root argument is changed in the set of arguments for a root signature, the hardware driver has to make a copy of the entire set of root arguments. What this allows is for the GPU to have multiple operations like draw calls in flight, each referencing their own unique version of arguments. So that's quite a convenience for an application while maintaining parallelism in GPU execution. Now, this is in contrast to all other memory types in DX12, like descriptor heap memory, buffer resources, textures. none of which are versioned by the hardware. There's just one copy of the data. So again, the way to think about what the hardware is being asked to do is the number of root parameters in a root signature is the amount of data that has to be versioned no matter how few of the arguments change. But if you think about the hardware that has this native root argument space, if you change a parameter that happens to live in the native space, then only that amount of space actually has to be versioned, while the spill memory, which hasn't changed, doesn't have to be versioned. It's a minor distinction. So how much root argument space do you get? DX limits the maximum root argument space for a given root signature to 64 D words. It's an arbitrarily chosen limit that's there to enforce the design philosophy for this space, which is that it's not meant for bulk data. That's what the descriptors and descriptor tables are for. And remember from the previous slide that when a given root argument changes, the entire root argument space has to be versioned for the hardware. So having a huge root signature and just changing individual parameters will explode memory usage unreasonably. So the actual costs of the types of parameters you can put in the root signature are as follows. Root constants cost 1 D word times the number of constants, since it's a set of 32-bit constants, so float 4 is 4 D words. Root descriptors cost 2 D words because they're a 64-bit GPU virtual address. Descriptor tables are actually only a single D word, and that's because those can get away with being just a 32-bit offset into a descriptor heap. Descriptor heaps are actually bound on command lists, and descriptor details for that are described a bit later. Finally, there's static samplers, which don't have any cost in the root arguments because, by definition, those are just baked directly into shaders. We can compare the various types of root parameters by their argument access latency. In particular, we can think about it in terms of number of indirections to memory. So for root constants, those can live directly in the root, and so that would be like 0 indirections to memory, particularly for hardware that has native root argument storage. Root descriptors would be considered 1 indirection to memory because what's in the root is the descriptor, which contains a pointer to the actual data. You can think of descriptor tables as then being 2 indirections to memory. The first being following the pointer to the descriptor, to the location in a descriptor heap, and that's the descriptor table pointer. The second indirection then is following the pointer in the descriptor to the actual resource, like texture 2D data in memory. And you can think of adding an additional level of indirection for hardware that has a native root if the root argument in a large root signature has to live beyond the native root storage space. So you can think of more indirection as obviously slightly more access latency. Depending on the scenario, though, or the hardware characteristics, these varying levels of access latency may or may not be actually noticeable. Another way to look at what these extra levels of indirection buy you is that the more indirection you go with, the sort of larger amount of memory you have at your disposal, and the more flexibility you have in the memory layout, such as using, the full breadth and richness of descriptor types. Given the details about how various hardware implements root arguments, here are some general guidelines for how to structure a root signature in a way that will work well for the breadth of hardware. Of course, if you're interested in having custom code paths for specific hardware architectures you care the most about, you're free to do so, but at least as a catch-all, or if you want to have one code path for all, the guidelines described here should be generally good. First of all, you want to try to have as small a root argument footprint as is reasonable. And there you're just going to be striking a balance between the convenience and flexibility of having a larger root argument footprint versus the benefit of a smaller footprint in it being easier for the hardware to version the arguments. Now, for any size root signature, but large ones in particular, you want to order the parameters in the signature declaration first to last, roughly in order of highest to lowest frequency of expected change. One exception to that is if you've measured that the access latency for a given parameter is needs to be as low as possible, even if that parameter wouldn't change very often, so otherwise you'd put it near the end of the root signature, push it earlier in the order. Some other advice would be to, if possible, use root constant buffer views, root constants as well, rather than putting constant buffer views in the descriptor heap. There's some hardware that really does prefer having constants more directly in the root argument space. Another thing to do is try to use the root signature flags that were described earlier that allow turning off particular stages from having root visibility. So for some hardware, there's efficiency to be gained by not having to pass parameters to shader stages that don't need them. GPUs that support DX12 fit into one of 3 tiers of resource binding support, where the higher number tiers represent hardware with fewer constraints, and therefore more flexibility in the bind model. One property that's common amongst the tiers is the size of descriptor heap that can be created. They all support creating descriptor heaps of up to 1 million descriptors in size. Tier 3 allows going even further. What differs amongst the binding tiers is the number of a given descriptor type that can be visible per shader stage in the root signature. So taking constant buffers, for example, on tier 1 and tier 2 hardware, at most 14 constant buffer views can be visible per shader stage, like from a vertex shader, for example. So the way that is enforced is when a root signature is declared, the sum of the constant buffer views across all descriptor tables visible to a particular shader stage can't exceed 14 in this case. UAVs have a slightly different constraint in that the total number of descriptors is actually a limit that applies across all shader stages. So for feature level 11 hardware, that's resource binding tier 1, if the vertex shader had visibility of 4 UAVs and the pixel shader had visibility of 5, that would be 9 UAVs in total, which exceeds the limit of 8. So it's a visibility, it's a sum total across all shader stages as opposed to per stage for the other descriptor types. For the hardware at the higher tiers that support full heap for the number of descriptors per shader stage, this is an indication of hardware that truly implements descriptor tables as just a pointer into the descriptor heap, and the hardware is able to index off that pointer all the way through the entire size of a descriptor heap. In contrast, for the boxes in this table where the numbers aren't full heap, the hardware that has these constraints actually has to implement binding of these resource types manually in sort of an emulated way, so it isn't as clean as just a pointer into a descriptor heap. Even though the API This shows how to query the resource binding tier through the D3D API using the check feature support API. You're now going to see several example root signatures, giving you a sense of the huge range of possibilities at your disposal for organizing, grouping, and managing the sets of resources and data that your shaders can see. The degenerate case would be a root signature with no parameters. Now, you're unlikely to use this, but at least as a thought exercise, note that even with no parameters in the root signature, there's still some resources available to the shader pipeline, like the input assembler and render targets depth. Here's an example of a simple root signature consisting of just a single parameter, in this case, a root constant. What's also shown in this diagram are a few of the other interesting parts of the root parameter declaration. For example, the HLSL bind slot, where the shader will see the root parameter show up, as well as the API bind slot, where the root argument for this parameter can be bound at commandless record time. The numbering of the API bind slots is implicit based on the order of the parameters in the root signature. So the first parameter is always API bind slot 0. And so here we see an example of how one might bind the root argument for this parameter at commandless record time. In this example, it could be a seed value that's perhaps used in the shaders to procedurally generate something. Now, the fact that you see a uint here in this declaration is actually not relevant to the hardware at all. In fact, it's not even part of the root signature declaration. It's just shown here because it's something you as an application know that you want to put in this parameter. This root signature consists of a couple of root constants and a root descriptor, in this case, a constant buffer view. You'll note that the height of the root descriptor is depicted as twice that of each of the individual root constants, and that's just a visual indication of the fact that root descriptors cost 2 D words in the root signature, and that's because a root descriptor is a 64-bit GPU virtual address. So in this case, this root signature has an argument footprint of 4 D words. At the bottom, you see an example of how one would, at commandless record time, set a root constant buffer descriptor. In this case, since the API bind slot is slot 2, you see the 2 here. And this example is illustrating the notion that perhaps you have a large buffer in memory where you're appending constants to be used for each draw call. And so for a given draw, you would set the GPU virtual address where the current draw's constants start, and they will show up in the shader at bind slot B0 as a constant buffer view. This root signature contains a couple of descriptor table declarations, the first of which is a range of 2 SRVs followed by a range of 2 CBVs followed by a UAV. At execution time, the descriptors for this table will reside in a CBV, SRV, UAV descriptor heap. The other descriptor table is a range of 2 sampler descriptors, and execution time, those show up in a sampler descriptor heap. As an example of binding a descriptor table on a command list, here we see the first descriptor table, the one at API slot 1, being bound to some location in a descriptor heap. And so if you imagine some large descriptor heap containing all kinds of descriptors, setting a handle to a particular location in a descriptor heap as a descriptor table argument tells the hardware to find, or a shader to find, in this case, this set of 5 descriptors in this range of the descriptor heap, starting at where the handle points. Another interesting part of this root signature is the first parameter, where we have a root constant that is 4 dwords in size. The example at the bottom here shows that we have the option of actually setting even just a subset of the constants. So in this float 4, suppose we wanted to just change the middle 2 arguments. That's what this example shows. So we're at API bind slot 0, and we're binding 2 constants at starting from offset 1. Here's a pretty dense root signature that has a little bit of everything in it. On the bottom you see a couple of static sampler declarations. For these, the full sampler state definition would be baked into the root signature and immutable. You also see that there's several descriptor table declarations. The reason you might find this useful is it allows you to organize your descriptors, for example, by frequency of change. So suppose you were at commandless record time filling in a descriptor heap with descriptors relevant to each new draw as you go. By organizing your descriptors by multiple descriptor tables, what this lets you do is, like, suppose you only need to change a couple of constant buffer views for a given draw call, and you want none of the other descriptors to change. What you would do is write the 2 new constant buffer views at some unreferenced location in the descriptor heap, set the descriptor table pointer for those constant buffer views to that location, and then just rely on the fact that all the other descriptor table pointers have already been initialized to point to various other locations in the descriptor heap that you've already populated with the descriptors that don't need to change. Another interesting aspect of this root signature is that there's a couple of descriptor tables that define arrays of descriptors of unknown size. The reason this works is that for some hardware, and that's hardware of resource binding tier 2 or above, a descriptor table really is just implemented as a pointer into a descriptor heap. And so the notion of an array of unbounded size just takes advantage of this property, so that when you are recording, when you're declaring a root signature, it doesn't matter to the hardware that you may not know what size an array of descriptors might end up being. Well, what the hardware will just do is, when you set a descriptor table pointer to some location in a descriptor heap, during within the shader you might index into this unknown size array, and all the hardware has to do is just offset the pointer and dereference whatever memory you arrive at. And the only burden on you as a developer is to make sure that at execution time, whatever location in the descriptor heap that you reference has already been initialized with a compatible type of descriptor. There's a final interesting quirk on this in this example, and that's shown in the bottom here. This is an example of descriptor aliasing. What you see here is a descriptor table that defines a range of 2 descriptors in a descriptor heap, but yet on the HLSL side of things there are 3 bindings that are populated: U3, U4, and U5. What happens is, in a descriptor heap, you've got a couple of UAVs that you've defined. The descriptor table points to those. The start of the descriptor table assigns U3, and the next one over defines U4 and U5 in this particular declaration. What this lets you do is, without having to change a shader, be able to broadcast, for example, one descriptor to multiple bind points. Or if you change the root signature, you could, to a different configuration, you could put unique descriptors at each bind point. This last example illustrates a particularly interesting scenario with the root signature that would only work with resource binding tier 2 or above hardware. This hardware supports declaring descriptor tables with ranges of descriptors of unknown or very large array size, as previously mentioned. What you could do in this scenario, for example, is create a very large descriptor heap, say 1,000,000 entries in size, ahead of time, and as you stream in and out textures or assets in your, for example, your open world game level, you would assign any given asset a descriptor at some fixed location in the descriptor heap. At the beginning of each command list recording, you would set the one descriptor table pointer in the root signature to the start of this descriptor heap. And then the way you would have shaders find the individual textures that they need to use is by identifying them, the offsets into the descriptor heap using various forms of constants like root constants or root constant buffer views. So basically, given in the shader, given, for example, a material ID, you can index into this one large array to arrive at whatever textures or whatever types of descriptors you want to access for a given draw. We'll now dive into the specifics about how root signatures are used at the API. There's a couple of places where root signatures show up. One of them is that you pass in a root signature to pipeline state object creation, and that allows shaders, the driver shader compiler, to hard code the details of the root signature in the actual shader machine code. The other place where the root signature shows up is the root signature itself is an API object that you can set on the command list. And when you do that, you're defining the currently active custom argument space or binding space where you can set the parameters for subsequent draw calls and pipeline state objects to use. So by the time you get to a draw or dispatch call, both the pipeline state, and which has its own root signature, and the currently bound root signature at the API must match each other. Otherwise, results are undefined. When you change a root signature on a command list, it makes all the current root argument bindings undefined. One exception is if you set the same root signature over again, any previously set root arguments are still valid. Here's an example call flow during the recording of a command list. It illustrates the use of a couple of root signatures, setting of some pipeline state, setting some root arguments, and drawing. You'll see that the order that state is bound on the command list doesn't matter, as long as by the time draw arrives, all of the currently set state is self-consistent. The other requirement is that in order to be able to set root arguments on the command list, first a root signature has to be set to define a parameter space so that the arguments make sense. Okay, so let's dive into the example. First, we set a root signature. Then we set a pipeline state. And this pipeline state, when it was originally created earlier on, would have had the same root signature passed into it, so that when the driver compiled the shaders for the pipeline state, it could bake in the details of how to traverse the root signature data structure. Next, we call this function, which hides the details of setting up textures. One way that the application could handle this is filling in descriptors in a descriptor heap for the next draw. And this would be an operation that happens immediately on the CPU timeline, because descriptor editing can only happen by the CPU. And so these would be operations that are done on the device interface as opposed to the command list interface. But to correspond to that, what would be done on the command list is setting of a root argument, which is, in this example, say setting of a descriptor table. And what that does is by the time the command list executes on the GPU later on, that descriptor table pointer, in other words, a pointer into the descriptor heap, identifies to the shaders executing on the GPU where to find the descriptors representing the textures for the next draw. Next, we show just the setting of another root argument, in this case, a root constant. In this example, the application has decided it wants to have provide to its shaders a draw ID so that the shader knows which draw it is in the command list. In this case, it's setting a draw ID to the value 0. And this is a completely user-defined concept. Finally, we get to draw, and the point here is that, again, all of the state has to be self-consistent now, and so the currently bound root signature and corresponding arguments must match the root signature that was used when the pipeline state that's currently bound was created. Okay, next we want to set up for the next draw, so we change our draw ID to 1. Then we set a new pipeline state, and when we get to the draw, this new pipeline state must have been created with the same root signature that's currently bound, and it was bound up here. Okay, now we do something interesting. We set a new pipeline state, and then we set a root signature. This is different from the order we did it before, and that's totally fine. We then go and set some textures, and these are defining parameters in the new parameter space, a new argument space defined by this new root signature. When this new root signature was bound, all the previously bound arguments for the old root signature become stale. And so it's up to the application to define all the new arguments before the next draw. And so yes, by the time we get to this draw, the current root signature bound here must match the root signature used in the current pipeline state. Here we define how bundles work with root signatures. Now recall that a bundle is a variation of a command list that acts like a subroutine that can be called by a command list. And in fact, a command list can call a bundle multiple times or call multiple bundles, or multiple command lists can also call the same bundle. Now, as far as root signatures go, if a bundle sets a root signature that happens to match the root signature that the calling command list set before the bundle was called, then any root arguments that have been set on the command list flow into the bundle. They're inherited in. The bundle can then proceed to partially change some of the arguments. So it could choose to inherit some arguments and set other ones on its own. It could just completely inherit all the arguments, or it can replace all the arguments with its own arguments if it wants, whatever it wants to do. Another way to look at the way root arguments work on a bundle is anytime a bundle wants to be able to change root arguments, first it has to have set a root signature. And it's just that if the first root signature in the bundle happened to match the calling command list, that's when inheritance applies. But during the flow of a bundle, if a root signature is changed to a different one, then just like on a command list, changing root signatures invalidates all currently bound root arguments, and new arguments have to be bound for the new root signature. Now, going back to the inheritance aspect, the utility of this feature is that it allows a bundle to be parameterized. The inherited arguments are like a way of reusing the same bundle and having it operate different ways just by passing in different arguments. Now, a final interesting behavior to note is that when a bundle completes execution, the state of the root arguments at the end of the bundle flows back to the command list. And mirroring the way the root arguments work when flowing into the bundle, on the way out, if the command list that we return back to wants to change some of those root arguments, it can do so by first setting the same root signature on the command list as the last root signature that the bundle set. And so doing so, it can, again, choose to inherit all of the parameters, all of the arguments, change some of them, or just reset all of the arguments if it wants. Here's an example of the call flow of a command list calling into a bundle that was recorded earlier. First, in the command list, we set a root signature that defines a parameter space for root arguments. Then here we call a function that goes and sets up some descriptors and sets a descriptor table. And what we're doing here is setting up arguments that we want to actually pass into the bundle. The next thing we do is set a root constant, in this example some animation factor. And then we call the bundle. When the GPU is executing this, when it gets into the bundle, these arguments that we've just set will be inherited, as long as the bundle first sets the root signature to be the same one as the root signature we've bound here. So in the recording the bundle, as I mentioned, the first thing we do here is set the root signature, and it's the same as the one we want to have set just before calling this bundle, so that we can inherit bindings. Here we set a pipeline state that who was created with the same root signature that is bound. And so at this point, since we set the same root signature, we've inherited whatever the calling arguments are, and in this example that would be descriptor table and this animation factor. But we choose to set some of our own root arguments within the bundle. In this case, we set a draw ID, and then we do a draw that uses the inherited constants and the draw ID. And then after that, we go and change our draw ID to 1 and then draw again. So so this example basically illustrates the inheritance of arguments, as well as the ability of a bundle to change some arguments on its own. Here's a question that gets asked a lot, and that is, why is there a separate root signature API object from the pipeline state object? Or said another way, when a PSO is set on a command list, why isn't the root signature that's already a part of that PSO not just set on the command list at that time, rather than the application having to go and set the root signature separately? So for some background, it's helpful to consider exactly what's going on when setting pipeline state versus setting a root signature. In setting a pipeline state, all that happens is setting of the pipeline state on a command list. It's like setting a pointer on the hardware. Where the root signature comes in with a pipeline state object is actually earlier on, and that's when the pipeline state object is created, and the driver is compiling the shaders for the pipeline state. At that time, the root signature is used so that the generated shader code can bake in assumptions of where the needed root arguments will be. By contrast, setting a root signature at the API only serves to configure the command list to be able to handle the new custom parameter space that the root signature defines. In particular, that means all the root argument setting commands on the command list, like set graphics root descriptor table, for instance, know exactly what to do based on the current root signature configuration in terms of where to place that argument so that pipeline state objects will be able to find them. Okay, so given that background, still the question remains, why not merge these two steps, in that setting a PSO on the command list could also why not just also set the root signature that's part of it? Well, so here's some answers. One is that when recording a command list, the application may not initially know which PSO it actually wants to use. It might not have traversed that part of the scene graph yet to know which pipeline state it actually wants to use. but it still might already want to start binding some arguments, like maybe some global constants that might that the application might know it needs to bind regardless of what PSO gets set. And so by setting the root signature ahead of time, that means parameters can be bound even before the PSO is ready to be set. Another reason to separate the root signature setting on the command list from the pipeline state is to make the semantics of the call flow sensible to look at. So if you imagine seeing a set of pipeline state object set calls in some code that's recording a command list, if each pipeline state object, we know that each pipeline state object has a root signature inside it, but if you happen to set a couple of pipeline state objects that have different root signatures, one after the other, it's not visually obvious that one of them has a different root signature than the other. And the reason that's important is there's this property that changing root signatures invalidates all previously set root arguments. And so, because the new root signature defines a new parameter space. So if just setting a PSO implicitly sets a root signature, then looking at a call sequence of set PSO calls, it wouldn't be obvious that somewhere in the midst of those set PSO calls there's invalidation of root arguments. And so instead we prefer that invalidation of arguments explicitly happens, and that's only when set root signature gets called. This is a little API detail, and that is how to provide a root signature to pipeline state creation. One way to do it is that if any of the shaders that are passed in as parameters to the pipeline state object creation have a root signature embedded in them, details for that, how to do that, are described later, then that root signature is the one that's used for the PSO. If it turns out that different shaders passed into the PSO, like the vertex shader and a pixel shader, each have different embedded root signatures, that's invalid and the runtime will fail the PSO creation. If there's another option for providing a root signature, and that there's this explicit root signature parameter as part of the PSO creation struct, separate from the shaders. And that's an optional parameter. If it's passed in other words, if a standalone root signature is passed into PSO creation, then that overrides any root signatures that may have been embedded in the shaders that are part of the PSO. But it also means that passing in an explicit root signature allows shaders that don't happen to have any root signature in them already to be used in the PSO creation. What's invalid is to create a PSO without any root signatures anywhere in none of the shaders, and also not passing one in. Here's a summary of the various ways of editing descriptor heaps, the types of edits being creation or copying of descriptors. First of all, descriptor heap edits can only happen immediately on the CPU timeline. In other words, DirectX doesn't provide any way to record in a command list a descriptor heap edit that can later be played back on the GPU timeline. While technically it could have been possible for DirectX to support GPU timeline descriptor heap editing, it turns out that trying to do that while also supporting CPU timeline descriptor heap edits would have added quite a bit of system complexity and corner case gotchas. So DirectX just chooses to keep the model simple and limit descriptor heap edits to coming from the CPU only. With non-shader visible descriptor heaps, such as the descriptor heaps for staging descriptors, the memory is read-write from the CPU, and so therefore those descriptor heaps can be used as either source or destination for copy operations. By contrast, with shader visible descriptor heaps, the system tries to put these heaps in memory that is optimized for being write-only from the CPU, and read-only by the GPU. As a result of that, these descriptor heaps can only be the destination of a descriptor heap copy or creation. And finally, for the type of memory the system tries to put these shader visible descriptor heaps into, on many systems having discrete GPUs, that memory is a globally limited resource. And I'm going to discuss that a little bit more. In order to maximize both CPU write throughput as well as GPU read throughput on shader visible descriptor heaps, the OS tries to place these heaps in GPU local memory that's writable by the CPU with write combining. Now it turns out that on a lot of systems, even high-end ones, memory that has these properties is limited to only 96 megabytes globally across all processes. To put that in perspective, a descriptor heap with 1 million entries in it would consume 32 megabytes with descriptors that were 32 bytes in size, which is fairly typical. And even that quickly eats out of the total optimal memory available. So the advice for apps would be to just not make huge numbers of really large descriptor heaps. If you had to do this, or multiple processes are making large descriptor heaps at the same time, the OS has no choice but to fall back to slower system memory. It's just not great. The performance will suffer for everybody who ends up in system memory. Now, one thing that's unfortunate is the exact nature of this limit does vary quite a bit across systems, and we just haven't come up with a good way of expressing exactly what a given system's constraints are. So the advice here is just general. I've covered some of this already, that DirectX doesn't support GPU timeline descriptor heap editing, simply due to the system complexity it would have added. Now, if what you're trying to achieve is the effect of trying to queue onto a command list a change in descriptor selection, there are ways you can achieve that with the API as it is. One example of that would be to put the set of descriptors that you want to select from into an array in a descriptor heap. And then in order to select from which descriptor you want to use in the array, you could queue a constant buffer update on a command list of an index value that a shader can then use to index into the array to select the appropriate descriptor. Shader model 5.1, which is introduced in DX12, allows for descriptor arrays that would help solve this, and that's described elsewhere. One of the properties of this that's handy is that the constant buffer update that can be recorded in one command list that's separate from the command list that happens to read the value to do the indexing. So you could have a command list whose behavior is changed by the execution of another command list that can be queued on the GPU. This is an example of one of the APIs for creating a descriptor. You can see all of them in the D312 header. This one's for creating a shader resource view. So you pass in the resource that you want to create the view on, the description of the view with properties like which set of MIP maps you want the view to reveal. And finally, you pass in a descriptor handle for where to place the descriptor that's being created. And that can be anywhere in a shader visible or non-shader visible descriptor heap. You'll notice that a couple of these parameters are optional. The meanings of that are described later on. Here are the methods for copying descriptors around. Just like descriptor creation, these copy methods are immediate and can be free-threaded. This first method, copy descriptors, actually has a complicated set of parameters not shown here, which allow for all kinds of operations like gathering descriptors, scattering them out, or some combination of them all in one API call. But if you want something as a simple alternative, there's copy descriptor simple, which just copies one range of descriptors from a source to a destination location. In either of these cases, the source for a descriptor copy must always be in a non-shader visible descriptor heap. The destination, though, can be either in a shader visible or non-shader visible descriptor heap. Suppose you're recording a command list, and as part of that, you are setting descriptor table pointers into a descriptor heap as you go, perhaps for every draw call. When the command list is recorded, these descriptor table pointers are fixed and can't change. But the memory that they're pointing to in the descriptor heap is just memory, and it can be changed anytime before, during, or even after the recording of the command list. The one constraint, though, is that you can't change the contents of a descriptor heap while a command list referencing the location you're changing is submitted for execution and might actually reference that location. That would be a race condition. Here's the rules around setting descriptor heaps. First of all, you can only bind at most one of the mixed style descriptor heaps and at most one sampler descriptor heap at a time on a command list. And those bindings are actually shared between graphics and compute PSOs that you might be switching between on the command list. If you need to change descriptor heaps on a command list, the cost is that it might mean the GPU has to wait for idle, which means finish all, for example, shading operations that might be in flight on the GPU. So it's like a little bubble. Now, a way to hide that cost would be to limit your descriptor heap changes to being adjacent to other operations that might cause similar weights. And the most obvious example is limiting your descriptor heap changes to the start of the command list, for example. With bundles, you can only call set descriptor heaps at most once. And more specifically, the selection of descriptor heaps that you use in the bundle must exactly match the descriptor heaps that were last set on the calling command list. Now, if a bundle, it turns out, doesn't actually need to change descriptor tables, in that case, it doesn't need to set descriptor heaps. Here's a summary of various strategies for arranging all of the sets of descriptors that you'll need the GPU to traverse in the process of rendering all of the objects in your scene. The most basic technique would be to fill in a fresh area of a descriptor heap with all of the descriptors that the next draw call is going to reference. And so just before issuing the draw on the command list, you would set a descriptor table pointer pointing to the beginning of this range of descriptors in the descriptor heap. The downside to this technique is there's a lot of repetition of descriptors in the descriptor heap, particularly if there's a lot of similarity between the sets of descriptors that consecutive draws are using, because each draw is just writing all of the descriptors it's going to need into a fresh area in the heap. The upside to this is that there's no need to try to remember where descriptors might have been placed in the heap in the past. Of course, this technique is going to burn through descriptor heaps very quickly. You're kind of linearly allocating through them. So a critical aspect would be to have multiple descriptor heaps. For example, a set of descriptor heaps that are being referenced by command lists currently executing on the GPU that's separate from the set of descriptor heaps being used by command lists being recorded on the CPU. Another thing you could do is, with a large descriptor heap, potentially accomplish similar overlap by suballocating regions within a descriptor heap. A slightly more optimal technique than the above would be to pre-fill descriptor heaps with already known sets of descriptors arranged, for example, by object. So when you get around to recording a command list, all you have to do is set a descriptor table pointer pointing to the already pre-filled area in the descriptor heap. Another variation would be to treat the descriptor heap as one huge array where every asset in your world, for example, your tree texture, has a unique fixed location where it would go in the descriptor heap when it's streamed in. So the tree could always be in slot 742, for example. So suppose you had 10 textures that a given draw needs to reference. What you would do is pass into the draw 10 constants where each constant is the index in the fixed layout descriptor heap where to find the resources the draw needs to use. A technique that can be combined with the above ones is placement of constants in root constants and root descriptors wherever possible, particularly when these constants are changing at a very high frequency. For a lot of hardware, this performs pretty well and is preferred over putting constants in descriptor heaps if possible. The advantage of taking of putting constants in the root is you're taking advantage of the driver versioning, particularly for high frequency changes, that saves you from having to burn through descriptor heap for constants. Now in practice, where you might end up settling is some combination of all of the above techniques for whatever works best for even different parts of your engine or different subsets of the assets you're managing. You know, even something like if you just look at even the first technique here where that involved filling in fresh descriptors for each draw, by just having multiple descriptor tables, the amount of wasted space in the descriptor heap can be reduced by a large amount. In that if you've organized sets of descriptors by frequency of update, and you're only needing to change one set between two draws, you only have to write the fresh descriptors for the part that changed and change the corresponding descriptor table. There's a slightly annoying restriction that you have to worry about with certain descriptor types on resource binding tiers 1 and 2 hardware. So the descriptor types that this limitation I'm going to describe applies to are descriptor types that already are limited in another way, in that the total number of times the descriptor can show up in descriptor tables in a given shader stage is limited to a fixed number. An example is constant buffer views in resource binding tier 2, where you can only have at most 14 constant buffer views across all the descriptor tables that a given shader stage can see. So it's those types of descriptors with these fixed number limits that have an additional restriction that I'm going to describe. And the restriction is that any descriptor tables that you have in your root signature, when you actually use them on a command list, must be completely filled in the descriptor heap, even if some of the entries in the descriptor table won't actually be referenced by the shader. For example, if you have a branch that goes down a path that doesn't use some textures, in that case, you still have to fill in the descriptors for those textures in the descriptor heap. So the summary of the descriptor types that have this restriction are on resource binding tier 1 hardware, it's all the shader visible descriptor types, unfortunately. On resource binding tier 2, it's constant buffer views and unordered access views. And by the time you get to resource binding tier 3, none of this applies. So one small mitigation that makes this burden a little smaller is if you have a descriptor table that for a given draw you know you aren't going to reference some of the descriptors for, rather than having to come up with uh, real descriptors to put in those slots that you're not going to need, instead you can put in null descriptors into those slots. And there's a particular way that you actually have to make a null descriptor, and that will be described now. If you put a null descriptor in a descriptor heap, and then a shader accesses that descriptor, the effect that's achieved is as if nothing is bound. And the meaning of nothing is that there are sort of defaults for the behavior, such as reads returning zeros. The full details are elaborated on here. So now to create a null descriptor, you simply pass null as the resource pointer in the create view call, like create shader resource view and so on. The other thing you have to do is, as for the view description parameter in the create view call, you actually have to fill in the description with some sort of view configuration that hypothetically would have worked for the type of view that the shader is going to expect. The reason for that is some hardware will actually crash if, for example, the shader expects to find a texture 2D, but what you put in the descriptor heap is some other descriptor type, like texture 1D, even if that descriptor is a null descriptor. So basically you can have null descriptors as long as it's a sort of a typed null descriptor that's of the appropriate type for what the shader expects. The one exception to all this are root descriptors, since those consist of simply a GPU virtual address. So setting a null root descriptor as an argument in the root parameter space, and then dereferencing that from a shader is basically a page fault. What happens if you create a descriptor using a valid resource but null for the view description? What you get is a default descriptor in which the runtime auto-generates the view description in a way that covers the resource as much as possible. So if you had a resource with 14 MIPS, the default view on it would have 14 MIPS. This is really just an API convenience for a common case where when you're trying to make a view, it's an obvious covering of the entire resource. Being able to switch the root signature allows an application to use multiple binding conventions for different sets of shaders. For example, an engine may have multiple rendering passes or subsystems that each would benefit from having a custom bind space for the task at hand. The actual cost of switching root signatures is negligible. The command list just gets ready to receive a new set of root argument settings. Basically, the interesting bit is that after switching root signatures, all the previously set root arguments have now become undefined because there's a new parameter space. But even then, having to reset all the root arguments may not be a big deal, just depends on how many parameters there are in the root signature. So the upshot is it's probably okay to switch root signatures pretty often, especially if you're going to be changing all the root arguments anyway. You don't want to be doing it every PSO change though. It's probably the case that a lot of applications can get away with just a few root signatures for the entire application. And in some cases, even just a single root signature might even be fine. Recall that on a graphics command list, both compute and graphics pipeline state can be intermingled. So how does the root interact with that? Basically, the graphics command list has two parallel roots. There's a graphics root signature and the associated arguments, and then there's a compute root signature and its associated arguments. A compute command list, by contrast, just has compute state, obviously. These two sets of root signatures and arguments are completely independent of each other. So that's why there's set graphics root signature versus set compute root signature, set graphics descriptor table, set compute descriptor table, and so on. Whatever the currently bound PSO is, whether it's a graphics pipeline state object or a compute pipeline state object, determines whether it's draw calls that apply or dispatch calls in the case of compute. And correspondingly, the matching set of graphics or compute root arguments get referenced. Either set of root signatures or arguments can be switched at any time and don't affect the other set. What happens if you get something wrong? Like a shader expects an SRV at some location in a descriptor heap, but by accident you put a UAV there. Or you reference an uninitialized descriptor, and so on. Basically, the outcome is bad. The official statement would be that you get undefined results, including device reset. And undefined can even include, on some hardware, not even noticing that something went wrong, which can be particularly dangerous because if you don't test on the hardware that actually is sensitive to the mistake you made, you might never know you got anything wrong. The good news is the debug layer and tools are here to help, and they are getting better all the time. I won't go into too much detail about ExecuteIndirect, though its interaction with the resource bind model is a key component of this feature, so it's important to discuss here. Basically, ExecuteIndirect lets an app use the CPU, or in particular the GPU, to generate a buffer full of an array of commands. It's sort of like a simple user-generated command list. Each command in this command list contains, at the very least, a set of draw or dispatch arguments, like a vertex count. And in addition, an ExecuteIndirect command can optionally include a set of other state to apply. And currently, the set of state that can be included in a command includes vertex buffer views, index buffer views, root constants, and root descriptors. All of these have a well-defined layout. In other words, it's not hardware specific. So that allows an application to completely generate an ExecuteIndirect buffer on its own, any way it likes. Now, the actual layout of the individual commands for an ExecuteIndirect buffer is declared by something called the command signature. If a command signature is going to change any root arguments, the way that's defined is in terms of a subset of a root signature that's included with the command signature definition. When ExecuteIndirect executes, it inherits any state from the command list that the ExecuteIndirect commands themselves aren't going to change. At the very end of the ExecuteIndirect command, after the last draw or dispatch finishes, none of the state changed by the ExecuteIndirect command leaks back to the command list. There are two ways to author root signatures. You can use either method, whichever one you like. They're both functionally identical. The first way is to procedurally generate a root signature, which allows you to do so at runtime. And the second method is to author root signatures from directly within HLSL. Syntax for doing that is done in such a way that it's separate from the rest of your HLSL code. So you can #include the root signature to all the shaders that need it. Another option is to add root signatures to a shader using the FXC tool. Both of these options are discussed in a little more detail later on. Now, a key point in all of this root signature authoring is we intentionally designed this so that your existing HLSL assets don't need to know about the existence of a root signature at all, and they can still be used with a root signature. We know that a lot of developers have a lot of HLSL assets that are used across platforms, so we tried to avoid polluting the core of the language with the root signature concept. Here's a slightly closer look at the steps involved in root signature management. First, you'll see the couple of options for authoring root signatures that were mentioned previously. The programmatic method is the first, where you'd fill out a D312 root signature desk data structure. It's a little bit of a complicated data structure that benefits from the use of some helpers that live in D3X12.h for construction. Once you've made the struct, you pass it into D312 serialize root signature, and what you get out is a blob containing the root signature. Alternatively, you can use the HLSL root signature syntax, and details for this will be provided later. What you get out of that are either the same blob as the procedural method provided, or if you happen to compile a shader with a root signature as part of it, what you get is a blob that contains both the shader and the root signature together. So when it comes time to use the root signature, the first thing you do is you call create root signature, and that can take in either a standalone blob or a shader with a blob, and what you get out is an ID312 root signature interface. And that's what you later on set on the command list when you want to define the current argument space. Now you also pass in a root signature to pipeline state creation, graphics or compute pipeline state creation. And recall that the reason to pass a root signature into pipeline state creation is that driver shader compilers need to be able to bake in the details of the root signature data structure traversal directly into every resource access call site. So the options when you're calling create pipeline state for providing the root signature are either to have the shaders in the root signature have the shaders in the pipeline state already have the root signature combined, or you can pass in the ID312 root signature object that was created at the API. If you pass in the object and shaders that have root signatures, the object overrides. This is what a root signature declaration looks like in HLSL. It's a string consisting of a collection of comma-separated clauses. The example root signature declared here is illustrated in this diagram. Now I'll go through all of the entries in this example briefly, and the following slides will go into all of the options that are available in detail. This root signature begins with an optional declaration of root signature flags, and it's followed by a collection of root parameter declarations, where the order that the parameter declarations appear in this root signature defines the API bind slots where arguments for each of these parameters get set. So the first parameter that's declared here is a root constant buffer view, and you can see it in the diagram up here at API bind slot 0. So it's going to go to HLSL slot B0 space 1. Now this space 1 clause here is part of shader model 5.1, and that'll be discussed later. But briefly, what this optional space parameter allows is for this binding space B0, or the B register space, or same applies for the other ones, T, U, and samplers as well. The space clause turns the binding space into a two-dimensional number space, so it's not just B0, it's sort of B0, 1. The reason to have this is it allows multiple different declarations of the same register space to not conflict. So in this example, there's another constant buffer defined with bind slot B0, but the default space is space 0. So B0 down here doesn't conflict with this B0 up here. So you can have different parts of your code that have their own binding spaces and don't have to worry about colliding with other areas just by using different space numbers. There's another use for the space that I'll describe that will be actually not described here, but it's shown later. So the second root parameter is a root shader resource view that's shown up here. Then we have a root UAV at U0, API bind slot 2. The interesting part of this declaration is the use of the visibility clause, and in this example, this root descriptor is defined to only be visible to the geometry shader. The next couple of parameters define a couple of descriptor tables. The first containing a constant buffer view, a couple of UAVs, and interestingly, at the end of the table is an array of shader resource views of unknown size, and that's defined by using the unbounded definition for the num descriptors. You can use unbounded at the end of a descriptor table. And what this turns into is when you bind at runtime, when you set the descriptor table pointer into a descriptor heap for this descriptor table, from the shader, you can index into this array of SRVs as far as you want, as long as you've made sure that wherever you end up referencing descriptors in the descriptor heap, you've placed a valid descriptor. The second descriptor table here defines a couple of samplers that would end up in a sampler descriptor heap. Then we have a definition of a root constant. Another descriptor table, this one with a couple of UAVs. The interesting part of this example is there are two UAVs defined, or there's essentially a range of two UAVs that will be assumed to be in a descriptor heap where the descriptor table pointer is pointing, but slots U4 and U5 in HLSL will both get their binding from the same location in the descriptor heap. So this is a form of descriptor aliasing where a single slot in a descriptor heap can be bound to multiple bind points in a program. So by attaching different root signatures to the same HLSL program, you can change which types of textures go to any given binding. In this example, U4 and U5 get the same texture, but in another root signature you could place U4, you could bind U4 and U5 to independent locations in a descriptor heap or in a root descriptor. So finally, this root signature includes a couple of static sampler declarations, and they're just shown kind of off in the weeds over here. The static samplers are completely defined and in the root signature and immutable. Overall, you'll see a lot of these parameter declarations are making use of plenty of default parameters that make the authoring of the root signature relatively compact. In the case of the static sampler, you'll note that it's extensively using the defaults, and basically this is a completely default root static sampler. It's unlikely you would be doing this unless it turned out that all of the default parameters are exactly what you want. More likely you'd end up with something like this example where you're actually defining some of the parameters that you want your static sampler to use. Here's some examples of the root flags clause where the set of flags you want is ORed together. Not specifying this clause at all is the same as using root flags of 0. Here's the full set of flags that can be defined, and the meanings of all these are described earlier. Here's a root constant declaration. It consists of a count of constants, the HLSL register binding for it, where it shows up as a constant buffer view in the shader, and optionally a register space and shader visibility. Here's all the shader visibility options, the details of which are described earlier. These are the three types of root descriptor declarations, each consisting of the HLSL binding and then optionally the register space and shader visibility. A descriptor table definition consists of one or more descriptor table clauses, which I'll go into, followed by an optional visibility specifier, which applies to the entire descriptor table. each descriptor table clause defines a range of descriptors that appears in the descriptor table. Note that sampler descriptors can't be mixed in the same descriptor table as CBV, SRV, or UAV descriptors, but CBV, SRV, and UAV descriptors can be intermixed in the same descriptor table through multiple clauses. Each descriptor range includes the HLSL bind register for the first descriptor in the range, followed by an optional count of descriptors for the range, a register space qualifier that's also optional, and an optional offset. And this is an offset for where the range starts relative to the beginning of the descriptor table. I'll illustrate the way the offsets work with a little example. Suppose this is a descriptor heap and a descriptor table pointer at runtime is pointing to this location in the heap. So the descriptor table associated with this pointer defines what happens with how the shader will interpret the descriptors starting from where the descriptor table points and beyond, where each range in the descriptor table defines some area in the overall descriptor table. If all of the ranges in a descriptor table definition use the default offset of append, and this is the typical case, each range just appears contiguously from the beginning of the descriptor table. So if the first range defines 2 CBs, they would be expected to show up here. And if the next range defined 4 shader resource views, those would be expected to show up here when using the offset append. One of the things that being able to specify an explicit offset allows for is multiple ranges that overlap each other to allow aliasing of registers. So for example, multiple ranges of UAVs could both be defined at offset 0, for example, and that would mean that the HLSL bind slots for each range receive their binding from the same location in the descriptor heap. One of the options for num descriptors, this count, is the word unbounded, and that means that at root signature authoring time, obviously the size of an array isn't known, but it's basically up to the app at shader execution time to make sure that when indexing into the range of descriptors in an unbounded array, the shader never ends up referencing a descriptor that isn't correctly initialized in the descriptor heap. Finally, there's an example here that shows a full definition of a descriptor table with 2 ranges. The first range defines a constant buffer view that goes to HLSL bind slot B0, and the second range, which will appear immediately after the first one, defines register T3 and beyond, because the num descriptors is declared as unbounded. A sampler declaration starts with the HLSL register bind slot and then is followed by the sampler state definition. The available options and the values that can be set are self-explanatory if you look at the corresponding C++ version of a sampler description. They're functionally equivalent, with one exception, and that is border color, where when you define a sampler state that lives in a descriptor heap using the C++ method for creating a sampler state, the border color can have a full floating point per channel colors, whereas static samplers use a fixed enum for the selection of border colors, where the options are opaque white, opaque black, and transparent black. Here's an example static sampler declaration defining register slot S4 and assigning the filter to min-mag mip linear and relying on defaults for all the other parameters. Recall the example HLSL root signature that was shown earlier. It pound-defined the string root signature definition to the name myRS1. So here's how to attach that root signature to a given shader entry point in your HLSL program. You use the root signature attribute just before the entry point. When you do this, and you compile the shader compiler will verify the compatibility between the root signature and all the resources the shader program uses. The HLSL compiler provides a variety of options for manipulating root signatures that have been authored in HLSL, either using the command line FXC tool or programmatically using exports from the compiler DLL. Zeroing in on the FXC command line, the most simple example is to simply compile a shader, in this case with target PS51. Here's the shader program, and suppose that there is a root signature here. That's an optional thing. In this case, if there was a root signature in the program, this output binary now contains both the compiled shader as one blob and the root signature as another blob in the same binary. So from this binary RS1 that contains a shader and a root signature, one thing we can do is extract the root signature out of it using this command. So rs1.rs.fxo now is just a shader with no root signature. The other thing we can do is remove the root signature, leaving the shader. So rs1.strip.fxo in this example is now just a shader alone. Now if you have a standalone shader and a standalone root signature binary, you can combine them, as in this example, which outputs a new binary, rs1.new.fxo, that contains both the shader and the root signature combined. And so this is now the equivalent of the original rs1.fxo. And finally, if you just want to compile from a shader program a standalone root signature directly, there's a shader target called rootsig10 that will just compile the root signature into a binary, and in this case, you identify the name of the pound define for the root signature here. The exports from the compiler DLL basically allow similar functionality that the command line exposed. DX12